Hello there. In continuation of the previous video lectures, now we are going to be see how to find out the resultant force from the given distributed load. So as we have discussed about it, the distributed load, we don't have any proper methodologies or any kind of the equations are not available. But we are trying to convert that into the simplified into the equilibrium equations. As you know, even though the distributed load is going to be acting on a beam or maybe any kind of the object, it has its own equilibrium condition. So then by using that, we are going to be converting into the simplifying that equations. So simplifying the distributed loads, and then we are going to be calculating the resultant force which is going to be acting on a beam, as well as the reaction forces on the beam we are going to be calculating. So in that part here, determine the resultant force. So we need to find out the resultant force. So we need to calculate it. So then in this case, for this one, I have taken one arbitrary shaped distributed load is going to be acting on a beam. So that the name I am going to be giving A, and the B is going to be the beam is going to be spanning at a length of L. At the same time, it is going to be supported on a triangle as well as the roller, the shape on this part. And this is going to be the uniformly varying load I have taken for the simplification. So then the x-axis is going to be representing your length of the beam, and the y-axis is going to be representing the load of the beam that is going to be in terms of the Newton meter is going to be available. So then in this case, how we can going to be converted into the simplifying and finding the resultant component. For this one, I am going to be taking the one elemental strip on the beam. So on the distributed load. So I am going to be taking one elemental strip over here. So this elemental strip I am going to be say this is going to be the dx it is going to be. So that elemental strip I am going to be considering this is going to be the dx load it is going to be. So then how could you calculate the total load acting on this member? So for this part we are going to be considering, suppose if I am going to be taking the elemental load is going to be acting on the beam, that I am going to be taking the dw capital W, that is equal to, what is the formula we do have? That's going to be area we need to be taking. So that area is going to be, the height is going to be, the uniform distributed load is going to be W is available, and the thickness is going to be the dx is there. So that the omega, that's going to be small w into x we are going to be taking. This is going to be the elemental strip is going to be the load is acting on the beam. This is going to be the elemental. That means only this area is going to be suffering this kind of the loads. Now, what is the total length of the beam? The distributed load is going to be acting. It means that we need to substitute the limits in that in this equation, so that we will get it the total distribution load. If I am going to be substituting in this one, that I am going to be taking the total W. So integral 0 to L, this is going to be the distribution load, that's going to be taking the dx. This way we are going to be calculating the total load acting on the beam. So that means the total load is going to be acting on that beam, we will get it. So this way we are going to be calculating so that's we are going to be converting into the point loads, that's we are getting in terms of the newtons. But in this case, this is going to be the Newton per meter, we will get it. So here we have derived the resultant force is going to be acting on that member. So that means the total distributed load is going to be converted into the resultant force. The resultant force is nothing but a single concentrated force is acting on that member. So then in this case, what is going to be the final conclusion from in our discussion is that the total load acting on the beam. Here, what is the total load? That's going to be the capital W, that is equal to the area under the load diagram. What is here the load diagram here? So this is representing the load diagram. The total dots what I am going to be giving, that's going to be the load diagram. That means already we have discussed the load diagram is nothing but the distributed load is going to be on the length of the beam is going to be called the load diagram. This way we are going to be calculating. Now we will see how to find out at what location this distributed total load is going to be acting on that beam with reference to the A. So we have found out the resultant force is acting on the beam. So then how we are going to be simplifying this member? So then I am going to be taking the same beam, right? This is going to be the A, this is the B, and here is the rollers and the triangle edge support. And the same, somewhere the total load is going to be acting on this member. Can you see the total uniformly distributed load? Simply we converted into a point load which is going to be acting at the finite area on beam. Now we need to find out the location of this W with respect to the A or with respect to the B. How could you calculate it? Now here we are applying the first moment of inertia we are going to be applying over here. That's going to be the line of acting of the resultant force we need to be calculating. What is that? The line of action of the moments we are going to be taking here. The same we are going to be taking with respect to this part. So it is going to be existed at a distance of xc, suppose if I am going to be considering. That means xc is going to be the center of distance of this point load acting to the point with reference to the point A. So that I am going to be considering. We are going to be taking the moments at this A. So the take moments at A. So then what is going to be, we are going to be getting? This is going to be the resultant force is going to be acting in these directions. That I'm going to be taking W into the XC we are going to be taking, that is the force into the distance, that is equal to, already we do have, that is equal to 0 to L omega into the dx. That is going to be the uniformly distributed load we do have. So once we do have this one, so then we are going to be calculating the XC over here. See, this is going to be the distributed load. It is going to be existed at a span of X length, suppose it is going to be here. So then finally the XC is going to be the distance we are measuring from the A, that is going to be integral 0 to L omega dx into the x divided by omega. So this way we are going to be calculating the XC. That means the distance from the one reference point, that XC we have calculated. So this way we do have to find out the that line of acting, the line of action of the resultant force with respect to the one point. So from this discussion, what is the main outcomes? We are able to understand and how to determine the magnitude of the resultant force. So in this process we have learned how to convert the distributed load into a point load, and it's the point load means it has its magnitude as well as its direction we are going to be finding, and how to determine the line of action. It means what is the location from the reference point to the point of application. That means it is going to be the point where it is going to be, the load is going to be acting on the beam. That's we have discussed in this part. So with this one, I would like to say that thank you for your support.